Hey class, this is the last real lecture of the quarter. So it's still on chapter 10, but I'm gonna call it 10 bonus because I just took a couple of things from the last couple sections that were the most important, and instead of doing unnecessary things in the lectures, I just took the most important stuff and made it into one lecture. So the first thing we're going to talk about in this last lecture is the inverse of a matrix. So a big thing with the inverse is first we need to understand that there's a thing called the identity matrix. Which we call IN, and it is an n by n, a square matrix, with ones along the diagonal and zeros elsewhere. So for example, if we had I2, which is our 2 by 2, it would look like 1, 0, 0, 1. I3, which will be a 3 by 3, will look like 1, 0, 0, 0, 1, 0, 0, 0, 1. And I4 would look like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and so on. But the important thing to see is that we always have, whoops, this highlighter thing is not working like I want it to. Oh well. Is we have this nice diagonal of the ones. So this kind of works like the number 1 would work if we were working with numbers. So the identity matrix has the property that IN times a matrix A equals A, and B times IN equals B. So we can multiply it on the left or right, and it will just give us a matrix back out. And this is when the multiplication is defined. Like obviously, if A was a 3 by 3, we couldn't use a 2 by 2 with it. But it's basically the same thing as multiplying by 1, but for matrices. All right, and now we're going to talk about the inverse of a matrix. So if we let A, I was going to underline this with blue because it's kind of a definition. So if we let A be a square n by n matrix, so n rows and n columns, if there exists an n by n matrix, A inverse with the property A times A inverse equals the identity equals A inverse times A. Then we say A inverse is the inverse of A. So we don't always have an inverse for every matrix. There exists some matrices that don't have inverses, but if we do find one and it has this property, then we call it the inverse. And this is similar to if we were to, like with numbers, if we had 3 and we multiplied by 1 over 3, that gives us 1. So this 1/3, this is the inverse of 3. So we're doing a similar thing with matrices now. So if we do an example, we're going to verify B is the inverse of A. So where A is 2, 1, 5, 3, and B is 3, -1, -5, 2. Okay, so first we're going to look at AB. So this is going to be 2, 1, 5, 3 times 3, -1, -5, 2. So this is going to be, remember, we're going to multiply by doing row by column. So 2 times 3 is 6 plus 1 times -5, so -5. And then we're going to do row 1, column 2. We're going to do 2 times -1 is -2, and 1 times 2, +2. Then we're going to have row 2, column 1, 5 times 3. That is 15 minus 3 times, whoa, where'd that line come from? Okay, sorry. Okay, and then we're going to have 3 times -5, so that's a -15. And then we're going to have 5 times -1, -5, plus 3 times 2, +6. So simplifying this out, we end up with 6 minus 5 is 1, 2 minus 2 is 0, 15 minus 15 is 0, and -5 plus 6 is 1. Well, that is I2, which is what we wanted. Now we have to verify BA equals 3 minus 1 minus 5, 2, 2, 1, 5, 3. So now when we do it this way, we're going to have a 3 times 2 is a 6 plus a -1 times 5, so that's -5. Then we're going to have a 3 times 1 is a 3 plus a -1 times 3, that's a -3. Then a -5 times 2, that's -10, plus a 2 times 5, that's a 10. And then a -5 times 1 is -5, plus 2 times 3 is 6. And then when we simplify, we get 6 minus 5 is 1, 3 minus 3 is 0, -10 plus 10 is 0, and -5 plus 6 is 1. There we go. That also equals I2. So therefore, B is the inverse of A. Okay. So I'm only going to teach you guys how to find the inverse of a 2 by 2 because there's a simple formula for that. Solving for a 3 by 3, 4 by 4, like an n by n generic one, it takes a lot more work and we don't quite have enough time in this quarter. And you also will see it less compared to what the rest of the lecture is going to be on. So I'm just going to teach you about the inverse for the 2 by 2. So the inverse of a 2 by 2 matrix. So if A is A, B, C, D, just these generic terms, then A inverse equals 1 over A times D minus C times B times the matrix. So you're going to switch the terms on the diagonal here. I'm actually just going to write it. So we're going to switch these two terms. So we're going to get a D and an A. And then we're going to make B and C negative. So we're going to get a negative B and a negative C. And this only works if AD minus CB does not equal 0. Because then A has no inverse because we'd be dividing by 0, and that's undefined. So this is pretty important, this formula. I'll ask you guys about this on the homework and very likely on the final. Okay, and also something to know. Only square matrices, which are n by n, have inverses. Just think about it. If we had a and n an m by n, and we multiplied it by something like, if A inverse, this one would have to be an n by n. And then if you were to rewrite it, A inverse here, they would not match anymore. So that means your A's and your A inverses are always going to be square. Okay, so moving on, we're going to talk about the determinant. So if a matrix is square, or an n by n, then we can assign a number to it called its determinant. So determinants can be used to solve systems of linear equations. Oops. Sorry, I thought I had my phone on silent, but I did not. All right. All right. So it can be used to solve systems of linear equations, and they are also helpful in determining whether a matrix has an inverse. So first I'm going to teach y'all the determinant of a 2x2. So we're going to use that same A equals generic A, B, C, D. Then the determinant, we're going to call it, just abbreviated as DEET A. This is going to equal AD minus BC. And this might look very familiar because this is the exact thing we divided by up here for our inverse. I'm so sorry. My phone is on silent and it is just not staying silent. Okay. So, yes, so we found the determinant. And you might notice this is our diagonal multiplied together times or subtracted our cross diagonal product. So that's where we get our AD. It's our main diagonal, and then we're subtracting our off diagonal, the C times B. All right, now we're going to do an example. We're going to evaluate DEET of A for A equals 6, -3, 2, 3. So first we're going to do our main diagonal. It's going to be 6 times 3 minus our off diagonal, which is going to be 2 times -3. So this will give us an 18 plus 6 because the two negatives will cancel. And this is 24. So the determinant of this matrix is 24. Okay. Now I'm going to teach y'all how to take the determinant of an n by n matrix. So, and we're going to explain this through an example because it's really hard to do in generality. Because if I just throw a bunch of random letters at you, it won't make any sense. So we're going to work through an actual numbered example. So we're going to take a 3 by 3, 2, 3, 1, 0, 2, 4, -2, 5, 6. And for this example, we're going to be focusing on expanding around this first row. Later, I'm going to teach y'all that you can choose any row or column, but I'm going to start with this first row. So first, we must determine the sign of each term in this row. And it's not the sign of the actual number. No, instead, if we take our matrix and we start in this top left corner or the northwest corner, we're going to assign positives and negatives alternating, starting with plus and moving down. You see? So it alternates as we go. And then we're going to multiply these signs together to see the sign in each one of our blocks where our terms would be. So if we kind of divide it, where we'd have our slots be the same as where they would be above. Two positives make a positive and a negative, that makes a negative, and then two positives make a positive again. And we can do this all the way down. A negative and a positive is a negative and a negative is a positive, a negative and a positive is a negative, positive and positive is positive, positive and negative, negative and positive and positive. So in this little grid here, we now know the sign of each of these entries in our matrix above. So this means if we're starting with 2, because it's the first part of this row, we're going to rewrite our matrix. 2, 3, 1, 0, 2, 4, -2, 5, and 6. So we're going to start with 2. So the first thing we're going to do is we're going to write our sign down. And then we're going to multiply it by our number, which is 2. And now what we need to do is we're going to cross out the column and row that 2 is in, like this. And now we're just going to look at this little submatrix. Well, so now we need to take the determinant of this submatrix, which we know how to do because it's a 2 by 2. So it's going to be 2 times 6. I'm going to call this like A prime. So we're going to get +2 times the determinant of this other matrix, or actually, why name it A prime when I can just write in the matrix? Oops. Of 2, 4, 5, 6. And so the determinant of this is 12 minus 20. So for this one part of the matrix, we get 2 times -8, which equals -16. And we're going to remember that because we're going to use it again in a second. But now we're going to move on to our second term in our row, which is our 3. So if we write 2, 3, 1, 0, 2, 4, -2, 5, 6. So this time we're going to be looking at 3. So our first thing is we're going to write the sign of 3. And if we look above at our block matrix, it is this negative value up there. So if we write negative, oops, I'm still in the highlighter tool, -3 times, and now we're going to do the similar thing. We're going to cross out the column and row that 3 is in, and then we're going to look at this little submatrix here of 0, 4, -2, 6. And again, we know how to take the determinant of a 2 by 2. So we're going to end up with -3 times 0 times 6 minus -2 times 4. So this is -3 times, this is going to become a +8, which equals -24. Okay, we're also going to remember this number. And now we're going to do this one last time for the last element in our row. So if we take a 2, 3, 1, 0, 2, 4, -2, 5, 6, we select our 1. So our first step again is we're going to write the sign of our number. If we scroll back up, it's going to be a positive sign. So we're going to do +1 times the determinant of, and we need to find our submatrix by crossing out the row and column again. So our submatrix is 0, 2, -2, 5. So then we're going to have 1 times 0 times 5 is 0 minus -2 times 2. This will be 1 times a +4. Yes, a +4. So this is just going to equal 4. Okay, so now that we've found all of our sub pieces, we're going to add them together. So we're going to add all of the pieces together. So that's going to be a -24. Oh, oops, I should start with the first number we got actually, which is a -16 plus a -24 plus a 4. And adding these all together, we see that this is a -40 plus 4 is -36. So d(a) equals -36. Okay. We could pick any row or column to expand around. And a helpful tip, pick the row or column with the most zeros. That'll help things cancel out nicer and you'll have to do a little less work. I just like to do it, but if you really get the system down for just expanding about the first row every time and you only learn that, that's also fine. Because it doesn't matter which row or column you expand about because you're going to get the same thing. So we're going to do the same matrix, but we're going to expand around row 2 and column 3. So I'm going to rewrite our A matrix just so you don't have to look up at your notes a whole bunch. So 2, 3, 1, 0, 2, 4, negative 2, 5, 6. Okay. So, and we're going to start with row 2. So our first trick is we're going to find, and I'm going to write it in a little smaller way this time, so that you'll see the sum and it'll look a little cleaner. But we're going to start with our sign of 0. So in this one, if we were to think about our, I'm going to move this down a bit so I have a little more room to write my pluses and minuses. There we go. Okay. Oops. Okay. So plus, minus, plus, plus, minus, plus. So you don't always have to rewrite a matrix of the pluses and minuses if you don't want. You can kind of do the math right here kind of with it. So negative times positive is negative. So we're going to have our negative of 0 times the determinant. And of this one, if we were to cross out the row and column, we would have a matrix of, oops. Okay, now that I've crossed it out, you can see it's going to be 3, 1, 5, 6. I don't want to rewrite the matrix the whole time, so I'm going to just use the same one. So remember, it's 3, 1, 5, 6. Okay, and I'm not going to evaluate this yet. I'm going to write out all of my terms. So now we're going to have a negative times a negative, which is a positive. So a plus 2 times the determinant of, and I sometimes will just like put a finger over each row and column so that I can see the remaining terms and write them down. But in this case, we're going to be crossing out these terms. So we're going to have a 2, 1, negative 2, 6 matrix. And again, I'm just going to get rid of those lines right now. So a 2, 1, negative 2, 6 matrix. And now for our last entry in the row, it's a negative 4. So we're going to write a negative 4 times our determinant of, and here if we were to cross out the row and column, we'd have a matrix 2, 3, negative 2, and 5. So 2, 3, negative 2, and 5. I'm sorry, it's getting a little cramped, but so this is all of our term. And now look at this bit here. We're multiplying by 0. So this whole thing just becomes 0. You don't have to worry about it anymore. So this is why it's nice to pick the row or column with the most zeros, because you just won't have to calculate the determinant for something. All right, and now we're going to have plus 2 times the determinant of this 2 by 2, which is 12 minus negative 2 times 1 is negative 2. All right, and then we're going to subtract 4 times the determinant of this 2 by 2, which will be 10 minus negative 2 times 3 is negative 6. Okay, and now evaluating, this becomes a 2 times a 12 minus negative 2 is a plus 2, so 14, minus a 4 times 10 minus negative 6 is actually adding 6, so it's going to be a 16. And so writing this out, this is a 28 minus a 64, which equals negative 36. This matches exactly what we got up here. So there we go. And now we're going to do it one more time, but we're going to go about column 3. So I'm going to give myself a little more room. Okay, so 2, 3, 1, 0, 2, 4, negative 2, 5, 6. So this time we're going about a column. I'm still going to write plus, minus, plus, plus, minus, plus. So starting out, the sign of, and I usually work top down for columns, similarly how I work left to right for rows. It's just what I like to do. You theoretically could pick any order, but I like to work in the rows going down. So the sign is going to be a plus. It's a positive times a positive is a positive. And then we're going to have a 1 times the determinant of, again, if we cross this out, we end up with a submatrix 0, 2, negative 2, 5. 0, 2, negative 2, 5. If we were in person, I'd like use the chalk eraser to go over the matrix to hide things, but alas. Okay, and now we're going to find the sign of 4 is negative times the determinant of this one. We're going to cross these out, and our submatrix will be 2, 3, negative 2, 5. 2, 3, negative 2, 5. And then the last sign is a positive again for our 6 times the determinant of, and if this one, if we cross these out, our submatrix is 2, 3, 0, 2. 2, 3, 0, 2. Okay. So now we have a 1 times the determinant of this is a 0 minus a negative 2 times 2 is negative 4 minus 4 times a 10 minus a negative 2 times 3 is a negative 6. Remember, you're subtracting the cross diagonal when you do these 2 by 2s. Then we're going to add a 6 times 2 times 2 is 4 minus a 0 times 3 is 0. Okay, now rewriting again, we're going to get a 1 times a negative 4, so that's a positive 4, minus 4 times 16 plus a 6 times 4. All right, so this becomes a 4 Yes, becomes a 4 minus 64 plus 24. And then this becomes, I did something slightly wrong. 0, 2, negative 2, 5, 2, 3, negative 2, 5, 2, 3, 0, 2. This should be a 64 plus 24. Just trying to double check my math in my head. So if we were to add these together, we end up, oh yes, we end up with 4 minus 40. There we go, which equals 36. And the math in my head, I was getting a 34, and I was not happy about that, but negative 36 is what we wanted. So we have negative 36, negative 36, and negative 36. So we've now checked 3 times, and we are very certain that the determinant of this matrix up here is negative 36. So the last thing we're going to learn about in this class is going to be the invertibility criterion. This is pretty important. And if we had had more time, I would have done another lecture about invertibility, focusing on how to find it, but alas. So if A is a square matrix, then A is has an inverse. An inverse if and only if the determinant of A does not equal 0. This is very important. I'll be asking you guys on homework problems and very likely on the final if a matrix is invertible or not. And if it's a 2 by 2, I can ask you to find the inverse because I gave you that nice formula up above. But I might give you something like a 3 by 3 or a 4 by 4, and you'll need to find out if the determinant is 0 or not. And then you can tell me if it has an inverse. So This is very important. You guys need to remember this. And that's our last theorem for the class. Congratulations on getting through 117. All right. Bye, class.